everyone. Now we are going to start fourth application of Gauss theorem, electric field intensity due to uniformly charged hollow spherical shell. Hollow charged spherical shell, just like football, volleyball you can say. So we have to find out electric field intensity by using Gauss theorem. So consider here we have a sphere. This is not circle, this is what a sphere 3D, over which plus q charge is uniformly distributed over this surface having radius r. Now in this application we have to take three cases where we have to find out electric field intensity. The first is electric field intensity outside the shell, hollow shell, outside the shell. Let us suppose we have to find out electric field intensity at this point P at a distance small r. We remember capital R is the radius, small r is the distance of observation point. That is, we can write R is greater than capital R. So at this point we have to find out electric field intensity. Now with the help of Gaussian surface we can find out the electric field intensity. So we have to draw a Gaussian surface that will enclose this spherical shell, charged spherical shell. This is our Gaussian surface. This is our Gaussian surface. This is our first step to find out the electric field intensity. So now next step, here we have to consider a area vector. At this point P we have to consider a small area vector ds, and this is the direction of this area vector, and you know that this is the positive charge. Due to this positive charge electric field is outward. This is the direction of electric field also. The theta that becomes is equal to 0 degree. I think this diagram is clear to all of you. Now according to Gauss theorem, the surface integral of electric field over closed surface is equal to q upon epsilon naught. Now this dot product is removed by cos theta. Now you know that the electric field over the surface, over the Gaussian surface, that remain constant, mean magnitude that remain constant. Here electric field magnitude that remain constant over the Gaussian surface, but direction is different. Because here direction is this side. At this point direction is this side. At this point direction is this side. Magnitude that remain constant. So this is E. What is magnitude? This magnitude is kept outside the integration, and this cos theta, that is cos 0 degree, that is equal to 1. So now the integration of this area vector over the whole surface, that become 4 pi r, small capital, here 4 pi r square. This is the whole area of this closed surface, that is 4 pi r square, where r is the distance, r is the radius of this Gaussian surface, the 4 pi r square. So we can write here E into 4 pi r square q upon epsilon naught. So E is equal to 1 upon 4 pi epsilon naught q upon r square. This is the electric field intensity outside the surface. And in previous topic we have studied that this is the electric field due to a point charge, point source charge. This derivation already we have did by using Coulomb's theorem, by using Coulomb's law. So this is electric field due to a point source charge. So we can say that the spherical shell behave like a point source charge for outside observation point. Mean from this point, this spherical shell behave like a point charge. Now second is on the surface of spherical shell. This is the second case. Now we have to find out the electric field on the surface. Now this is capital R. Now on the surface we have to find out the electric field. At this point we have to find out the electric field that is on the surface. So now we have to draw the Gaussian surface just over the spherical shell. Over the spherical shell we have to draw the Gaussian surface whose radius also is equal to capital R. So here I will write small r is equal to capital R. So again this is small area vector ds, this and this is the direction of electric field. Theta again is equal to 0 degree. So simply in this equation we will replace small r with the capital R. Only this much. Only this. This small r is replaced by the capital R because on the surface this small r becomes equal to capital R. I think this point is clear. Now come to third case. Inside the spherical shell. Now this is the spherical shell over which plus q charge is uniformly distributed, whose radius is capital R. Now let us suppose at this point we have to find out the electric field intensity. So its distance from the center is small r. So here we will draw the Gaussian surface like this. Now because Gaussian surface enclosing no charge, that is q is equal to 0. Inside this Gaussian surface there is no charge. This Gaussian surface does not enclose any charge. So line integral of electric field over the closed surface is equal to q upon epsilon naught, and this q is equal to 0, so this term becomes equal to 0. Then further we will write E ds is equal to 0, but this term never be 0. This electric field becomes equal to 0. So inside the spherical conductor there is no electric field intensity inside this spherical shell. Now in the last we will do the variation of electric field intensity with respect to distance of observation point, where we have to find out the electric field intensity. Now this is the origin. Here we will take small r and here we will take electric field. Now as r is increases, I am drawing the spherical shell here. This is the spherical shell and this is the center O and this is the radius capital R. So up to this distance here R become capital R. So from 0 to small r, here electric field is 0 because we are inside the shell. Here inside the shell electric field that is equal to 0. So here electric field is 0. Now at R is equal to R, the electric field become maximum. Electric field become maximum here, that is E maximum electric field. E maximum electric field. After that, electric field, as we are going outside the surface, electric field decreases. So electric field will decrease in this way. Here electric field is inversely proportional to R square. So this is the graph. This is the variation of electric field with respect to distance R, and E maximum electric field, that is what? That is 1 upon 4 pi epsilon naught Q upon R square. Now you know that this I will write Q A and epsilon naught, because A is equal to 4 pi R square, that is the area, and Q upon is equal to sigma. Sigma is the surface charge density. So this is the maximum electric field. So this I will write here sigma upon epsilon naught. So this is the variation of electric field intensity with respect to R. So stay safe, be positive, and don't give up. Revise this topic. Now our applications are over. Next time we will solve some numerical, then start our next chapter. Thank you.